On June 1st, 2025, Ukraine launched 117 small drones from cargo trucks parked inside Russian territory. These weren't cruise missiles, they weren't stealth aircraft, they were cheap first-person view drones, the kind hobbyists fly on weekends for fun, and they hit Russian air bases hundreds of kilometers from the front line. Strategic bombers worth $500 million each, burning on the tarmac. The bases had radar, they had interceptors, they had billions of dollars in air defense coverage. And yet the drones got through, not because the system was weak, but because it literally couldn't see them coming. In the next 60 seconds, I'll draw you the blind spot every air defense system on Earth has. It's called the radar horizon. And once you see it, you'll understand why range on a brochure can be almost meaningless at low altitude. Most people imagine air defense as a giant invisible dome, a force field stretching out from a central point protecting everything beneath it. Anything that enters the dome gets detected, tracked, and destroyed. That's the image that defense contractors deliberately sell to governments. That's what politicians believe when they approve billion-dollar budgets. That's what the general public assumes when they hear about advanced missile systems protecting critical infrastructure. And that picture is completely and fundamentally wrong. In reality, air defense coverage is more like a collection of overlapping flashlights, strong in some angles, weak in others, bright at certain distances, dim at the edges. Point all your flashlights in one direction, and you've got a blind spot behind you. Point them outward, and there's a gap in the middle. No matter how you arrange them, you can't cover everything equally. And the weakest spot, the angle where every flashlight struggles the most, is close to the ground. Radar sees in straight lines. The Earth doesn't. That fundamental mismatch between radar and terrain creates a hard physical limit, the radar horizon. Beyond that point, the radar physically cannot detect low-flying objects, not because of any technical failure, not because the equipment is outdated, but because the planet itself is in the way. The Earth's curvature blocks the line of sight. Its geometry, pure and simple physics. No amount of money or advanced technology changes the shape of the planet we live on. Here's the math. A radar mounted on a 75-foot tower, that's about 23 meters, has a horizon of roughly 19 kilometers against a target flying at sea level. That's it. 19 kilometers of warning before something hugging the ground reaches you. Put that same radar a mile high, and the horizon extends to approximately 160 kilometers, assuming standard atmospheric refraction. Better, but still finite, still absolutely limited by the curve of the Earth beneath it. Now watch what happens when a drone or aircraft drops below that horizon line. It vanishes from the radar screen, not because of stealth coatings, not because of electronic jamming, because of geometry. The radar beam passes overhead, and the target slips underneath, hidden in the shadow zone between the horizon and the ground. At low altitude, you don't need stealth, you just need geometry. This shadow zone is exactly where threats have always hidden throughout the history of aerial warfare. During the Cold War, NATO pilots practiced a technique called nap of the earth flying. They would skim at 50 feet above the ground, just 15 meters, at speeds over 500 miles per hour, threading through valleys, following riverbeds, using hills and forests as natural cover. The goal was simple: stay beneath the Soviet radar horizon until the last possible moment, then pop up, deliver weapons, and disappear again before anyone could react. It required elite pilots, years of intensive and dangerous training, specialized aircraft equipped with terrain-following radar systems. It was extremely dangerous. Pilots died practicing it regularly, and it was expensive. Only the best-funded air forces in the world could afford the capability. Today, a $3,000 drone does the same thing. Autonomously, no pilot required, no years of training, no specialized aircraft needed. Modern drones don't need elite training to fly through the shadow zone. They need a flight plan programmed into cheap civilian GPS. They need a basic motor that can sustain low-altitude cruise for a few hundred kilometers. They need to stay low and follow the terrain. And because these drones are small, often with radar cross-sections comparable to large birds, even when a radar does catch a momentary glimpse, the return signal blends into ground clutter. Trees swaying in the wind, flocks of birds moving across fields, vehicles on highways. Everything near the surface creates noise in the radar picture. A small drone hiding in that noise becomes almost impossible to distinguish from the background environment. This is why cheap drones penetrate networks designed to stop threats costing millions. It's not magic. It's not some secret technology. It's the systematic exploitation of physics that hasn't changed since radar was invented 8 decades ago. The numbers tell the story clearly. In 2024, Russia was launching around 130 Shahed-type drones per week against Ukrainian targets. These are Iranian-designed loitering munitions, relatively slow, relatively simple in design. By early 2025, according to detailed analysis from CSIS, that number had climbed past 1,000 launches per week, a nearly tenfold dramatic increase in less than a single year. The drones don't need to be invisible. They don't need to outrun interceptors. They just need to stay low, stay cheap, and keep coming in numbers that overwhelm the defense. And here's what too late actually means in practice. Let's say the radar does detect a low-flying drone. Maybe it crested a ridge. Maybe it climbed slightly during a navigation correction. The system finally sees it on the screen. Now what? The kill chain, the sequence from detection to destruction, is not instant. It's a process, and every step takes precious time. First, the system has to confirm the track. Is this actually a drone, or is it a bird, a weather anomaly, a false return from ground clutter? You need multiple radar sweeps to build confidence that you're looking at a real threat moving in a threatening direction. That takes seconds, sometimes tens of seconds. Then you assign a weapon. Which battery is in position to engage? Which missile type is appropriate for this specific target? Is this target worth an interceptor that costs $100,000? Or do we wait and see if it's actually headed somewhere important? More seconds tick away while humans and computers make critical decisions under pressure. Then you launch. The missile leaves the rail. It has to accelerate to intercept speed. It has to fly to the intercept point. Even at Mach 3, that's not instantaneous when the target is kilometers away. Let's do the math on a typical scenario. A drone flying at 150 kilometers per hour gets detected at 20 kilometers. That gives you roughly 8 minutes until impact. Sounds manageable, but detection doesn't equal engagement. By the time you've confirmed the track, assigned the weapon, launched the interceptor, and the missile has flown to the target, that 8-minute window has shrunk dramatically. If anything in the chain hesitates, a moment of confusion, a busy operator, a system handoff between units, the drone gets closer, and closer still. Now consider faster threats. A cruise missile traveling at 800 kilometers per hour detected at 30 kilometers gives you just over 2 minutes total for the entire kill chain. If detection is delayed by even a few seconds because the missile was flying low in ground clutter, that window compresses to almost nothing. The blind spot isn't just about not seeing, it's about seeing too late to do anything about it. So if everyone knows about the radar horizon, why hasn't anyone fixed it? The answer is that every solution creates new problems. There's no free lunch in physics. Put your radar higher, and you extend the horizon. Mount it on a hilltop. Put it on a tall mast. The math improves considerably, but higher also means more exposed. That elevated radar station is visible for miles around. It becomes a priority target for enemy missiles, drones, or special forces. You've improved your coverage by making your sensor more vulnerable to being destroyed in the opening hours of a conflict. Coverage isn't blanket coverage. A single radar can only look in so many directions at once. Even modern electronically scanned arrays have limits. You might have excellent coverage in one sector and significant gaps at low altitude in another direction. Terrain makes this considerably worse. Every hill creates a shadow. Every tall building blocks a sightline. Urban environments are the worst. Forests of concrete and steel creating blind spots everywhere you look. The obvious answer is more sensors. Fill the gaps. Build a dense network of radars covering every approach at every altitude. But radars are expensive. Operators are expensive. Maintenance is expensive. Communications networks to link everything together are expensive. Most countries simply cannot afford to fill every gap. They make strategic choices. They prioritize certain areas and accept calculated risk in others. And adversaries study those choices very carefully. Here's where the defense industry marketing collides head-on with operational reality. FOI, Sweden's respected defense research agency, analyzed Russian air defense capabilities in detail and noted that against low-flying maneuvering targets, the S-400's real engagement range can drop dramatically, in some scenarios to around 20 kilometers. The brochure says 400 kilometers of range. Geometry says it depends entirely on altitude, terrain, and whether the radar can actually see the target. Against a high-flying aircraft with a large radar signature, sure, maybe you get that long-range performance. Against a drone hugging the terrain at 30 meters altitude, you might not see it until it's almost on top of you. This isn't about Russia. This isn't about picking sides. It's about physics that applies to everyone equally. Every air defense system on Earth, American Patriot batteries, Chinese HQ-9 systems, Israeli Iron Dome, fights this same fundamental constraint. The geometry hasn't changed since radar was invented during World War II. What has changed dramatically is access to the tools that exploit it. 50 years ago, Penetrating the shadow zone required elite military pilots, multi-million-dollar aircraft, and sophisticated terrain-following systems that only superpowers could develop and maintain. Today, it requires a cheap drone, civilian GPS, and some basic programming knowledge. The barrier to entry has collapsed completely. A pre-programmed drone flying nap of the Earth costs a tiny fraction of the interceptors meant to stop it. The economics have fully and completely inverted. The results are visible in the wreckage scattered across airfields. In 2025 alone, Ukrainian drone strikes destroyed over $1 billion worth of Russian military aircraft, high-performance fighters, strategic bombers capable of carrying nuclear weapons, attack helicopters, transport planes essential for logistics, sitting on airfields that were supposedly protected by some of the most advanced air defense systems in the world, not because those systems were fake or broken, but because cheap drones flying low exploited a gap that physics guarantees will always exist. Air defense doesn't fail because systems are weak. It fails because visibility has limits, and those limits are written into the shape of the Earth itself. Next video, the second blind spot. Saturation. How cheap drones arriving in mass can overwhelm even the defenses that do see them coming. How the economics of air warfare have flipped completely upside down, and what it means when a $1,000 drone can force your enemy to spend $100,000 to stop it every single time. But here's the question I want you to answer in the comments. If you ran air defense for a major military airbase, what would you fix first? Would you invest in more sensors positioned to see low-altitude threats coming? Or would you pour resources into developing cheaper interceptors that can kill cheap targets without bankrupting your defense budget? That fundamental trade-off, detection versus affordability, is the entire future of this problem. It's the question every military planner is wrestling with right now. And I genuinely want to know what you'd choose and why you'd choose it.